LEGO, learning egocentric action frame generation via visual instruction tuning. Imagine you were learning a new skill, or working on an unfamiliar task. Wouldn't it be helpful to get instructions on how to perform the task? This skill transfer from a knowledge source to a human user is very important in helping humans learn new skills. For example, let's say you wanted to wash the trouser in your hands with a brush, but you're not sure how to do so. Perhaps you ask a large language model, as they are a valuable knowledge source. However, when you ask it how to accomplish such a task, it responds with a set of general instructions that may not contain details that are applicable to your current situation. In other words, a user prompt of just text may not capture the full context. An egocentric snapshot of your current viewpoint may be helpful in capturing more context to an LLM, and as such, a visual large language model can respond with more specific guidance based on an input prompt of both text and image. Still, a purely textual output of instructions are not ideal for users to interpret and follow, because human brains process text slower than images. Visual cues can be more helpful, especially for visual learners. Therefore, we propose to directly synthesize an action frame, illustrating how to conduct the next action from the user's current egocentric perspective, set in the same situation and context. This generated action frame is more straightforward for users to follow and understand compared to responses from LLMs. This proposed novel problem is called egocentric action frame generation. The input is a user query regarding how to perform an action, as well as an egocentric image capturing the moment before the said action begins. The goal is to synthesize an egocentric image showing the execution of the action in the same context. There are two main challenges in this problem. First, the action labels in existing egocentric datasets are composed of only a verb and nouns. They are too high level and lack the necessary details for generative models to understand the actions correctly, and more detailed action descriptions are needed. Second, existing diffusion models rely on pre-trained clip text encoders to embed the text conditioning, but there is a gap between the domain of clip data and egocentric action data. The clip data includes more third-person images and fewer action descriptions, so even if the diffusion model is provided with the detailed action descriptions, the diffusion model may still fail to learn action because of limitations in the text embeddings. In this work, we propose our solution to these two challenges. First, we fine-tune a large language model via visual instruction tuning to curate enriched action descriptions. Second, we leverage the image and text embeddings from the fine-tuned visual large language model as additional conditioning to boost the performance of the diffusion model. Our work is closely related to two areas. First, our problem setting is similar to image manipulation, which has been studied in lots of prior work. Those approaches mainly focus on image editing related manipulations, such as replacing objects, changing the global image style, etc. But how to control the state change of actions from an egocentric viewpoint remains unexplored. Another relevant line of work is using LLMs in image generation. Prior work has explored how to leverage off-the-shelf LLMs to improve the quality of synthetic images without fine-tuning. In contrast, we investigate the contribution of visual instruction tuning in image generation. To conclude, we are the first to leverage LLMs to facilitate action frame generation in an egocentric perspective. We use GPT-3.5 to curate data for our visual instruction tuning, enriching the existing simple action labels into detailed action descriptions. Specifically, we select a few egocentric context image examples and use their action labels and the bounding boxes of relevant objects in the image as input to GPT-3.5. We also manually annotate the enriched action descriptions for these examples and input them into GPT as well. These manually annotated examples are used by GPT to learn how to generate similar enriched descriptions via in-context learning. The input query itself are then action labels and bounding boxes for the non-annotated examples. Finally, using the full input, including the in-context learning examples, GPT can respond with enriched action descriptions for the query action, scaling up our dataset curation effort to a larger dataset for visual instruction tuning. Our method is composed of two components. First, we introduce the visual instruction tuning. Given an input frame and the user text prompt, the image is encoded by an image encoder and then projected to the LLM feature space. Then, the image feature and tokenized text input are fed into a large language model. The LLM is trained to generate enriched action descriptions using the curated data from GPT 3.5. Note that the visual instruction tuning doesn't rely on any bounding box information, so once fine-tuned, it can generate enriched action descriptions for the remaining data at scale. After visual instruction tuning, we further leverage the image embedding after the projection layer for image generation. Similarly, the text embedding before the LLM linear head is also forwarded to the next component. For image generation, we first embed the enriched action description with a widely used pre-trained clip text encoder. Also, the image embedding from the VLLM is projected to the diffusion model feature space by a linear layer. And likewise, the VLLM text embeddings are also projected by another linear layer. However, these text tokens are generated auto-regressively by the LLM decoder, so each token only conditions on the context before it. We thus use two self-attention layers to learn the holistic semantic features. The input frame is encoded to a latent space by a pre-trained autoencoder and fed into a UNet with a Gaussian noise. All conditioning is fed into the UNet by cross-attention layers. Finally, we can get the generated action frame by decoding the UNet output to pixel space using a pre-trained decoder. We validate our method on two large-scale egocentric datasets, Ego40 and Epic Kitchens. Ego40 has the annotations of precondition 15 and point-of-no-return frames. We directly use them as the input and target images, respectively. Epic Kitchens doesn't have these annotations, so we empirically define the input and target frames. We also filter out data with low-quality frames, as well as data with too low or too high similarity between the input and target. Please refer to our paper for more details. We initialize the visual large language model from the Lava pre-training weights. We also initialize the text encoder, autoencoder, and UNet in the diffusion model from the stable diffusion checkpoint. The remaining parameters are initialized by the Xavier algorithm. We thoroughly evaluate our model using three categories of image-to-image similarity metrics. Different than prior work, which measured similarity between the input and output images, we measure the similarity between the generated images and the target frames, which better reflects whether the generated results can properly illustrate the resulting action execution in our problem setting. In terms of image-to-text metrics, we caption the generated image using the blip model, and then measure the generated caption's text similarity to the action descriptions. Before diving into the results of action frame generation, we first evaluate the quality of action description enrichment by a user study. The rater is asked to verify whether the action description from the VLLM is aligned with the actual action frames. The percent of aligned data samples on Ego40 and Epic Kitchens are 87% and 84% respectively. It suggests that the response from our fine-tuned VLLM is accurate enough for diffusion model training. For action frame generation, we first compare our model with prior image manipulation models. Our model outperforms all baseline models by a notable margin for all three contrastive pre-training based metrics: clip score, Ego VLP score, and Ego VLP plus score. In the other three metrics, our model also shows advantages in both datasets, outperforming on all but one metric. And though our model slightly lags behind Instruct Pix2Pix and FID on the Epic Kitchens dataset, it still achieves the second best performance. Next, we show the results of image-to-text similarity. Our model still exceeds all baselines in both datasets. The results indicate that our model can understand the action better and generate action frames that are more aligned with the action description. We further divide the actions into 4 bins according to the action state transition time, which is the duration from input frame to target frame. The flat curve suggests the egocentric action frame generation is equally difficult regardless of the transition time. Our proposed LEGO model still surpasses all baselines for all transition times. Considering the limitation of automatic metrics, we also conduct a user study with the 2 datasets. As shown in the example interface, we display to the rater the action, the input frame, and the 4 generated output frames from the 4 different models that we are comparing. We randomly shuffle the order of the 4 generated images to avoid potential bias. Each data instance is annotated by 5 raters. The user study results suggest that our model significantly surpasses the other models in win rate, which further validates our model's superiority in egocentric action frame generation. Additionally, we conducted a detailed ablation study to evaluate the contribution of each component. Using enriched action descriptions can improve the performance moderately compared to action labels alone, which supports our hypothesis that enriched descriptions can provide more details for action understanding. Then, both text and image embeddings from the VLLM can boost the performance by a large margin. This result validates our argument that the VLLM embeddings can complement the pre-trained text encoder in the diffusion model. Finally, after using both embeddings, the full LEGO model achieves the best performance on both datasets. We show that similar results can be observed in the PSNR metric. We also investigate the contribution of visual instruction tuning. Without fine-tuning, the VLLM image embedding does still help the generation performance. However, without fine-tuning, the VLLM text embedding appears to hurt the model. Compared to the models using fine-tuned VLLM embeddings, a notable performance drop is observed on all models. These results indicate visual instruction tuning is a necessary step for leveraging LLMs in the action frame generation. Finally, we share some visualization examples from our model. Here are the input frames before the action begins, and the user query asking about how to execute the action. And here are the generated action frames from our model. They semantically align with the user query and preserve most context from the input frames. We finally show the ground truth in our datasets. Our generated frames are very semantically similar to the ground truth, further validating the performance of our model. To conclude, in this paper, we introduced the novel problem of egocentric action frame generation to facilitate the process of skill transfer. We enrich egocentric action descriptions by visual instruction tuning to help the diffusion model understand the action state change from an egocentric perspective. We also propose a novel model, LEGO, that leverages VLM text and visual embeddings to improve the performance of the latent diffusion model. And finally, we conduct thorough experiments on the Ego40 and Epic Kitchens datasets to validate the superiority of our method and provide more insights to our model. Thank you.